Observational evidence relating to theories prior to the Big Bang is both intriguing and complicates the picture because it touches on the very nature of the origin of the universe. Although we cannot directly observe conditions before the Big Bang because of the constraints imposed by the event itself, various indirect observations and theoretical models convincingly support or refute ideas about the early state of the universe. One of the most significant pieces of evidence is the cosmic microwave background radiation, relict radiation that fills the universe and represents the afterglow of the Big Bang, supports the idea of a hot, dense state before the expansion of space and time. Measurements of temperature fluctuations in the cosmic microwave background provide a wealth of information about the early universe, including its density, composition, and distribution of matter. Some pre-Big Bang theories, such as inflationary models, emphasize rapid expansion, and observational evidence fits well with these ideas, reinforcing their plausibility. Another important piece of evidence is the large-scale structure of the universe. The distribution of galaxies and galaxy clusters gives an idea of how matter evolved after the Big Bang. Observations of the rate of expansion of the universe, especially through redshift measurements of distant galaxies, show that the universe is expanding. These data support the idea that the universe evolved from a very different state. Some pre-Big Bang models theoretically predict certain patterns of structure formation that can be compared to observed large-scale structures. However, not all observations are in clear agreement with specific theories prior to the Big Bang. Some problems arise from the entropy of the universe. The second law of thermodynamics says that the universe tends to increase in entropy over time. The idea that the universe arose from a highly ordered state prior to the Big Bang raises questions about how this high entropy fits with the observed low entropy conditions. Models proposing oscillating universes or cyclic models attempt to address this problem by assuming that the universe undergoes repeated phases of expansion and contraction, which offers an alternative to a single beginning. Although observations of the cosmic microwave background radiation and the structure of the universe support specific theories prior to the Big Bang, there remain unanswered questions and problems, especially with regard to entropy. Continued study and refinement of these observational data will continue to shape our understanding of the mysterious conditions that preceded the Big Bang. The cosmic microwave background radiation is a crucial piece of evidence that helps us understand the early universe. This surprising phenomenon represents an afterglow from the hot, dense state that existed shortly after the Big Bang, some 380,000 years later, when the universe cooled down enough for protons and electrons to combine to form neutral hydrogen atoms. This process allowed photons to travel freely, marking the moment when the universe became transparent to radiation. The cosmic microwave background serves several key purposes in cosmology. The uniformity of temperature across the sky indicates that the early universe was extremely homogeneous and isotropic as it cooled and transitioned from a hot plasma state. However, small temperature fluctuations are also present, revealing tiny variations in density that would later evolve into the structures we see today, such as galaxies and galaxy clusters. By studying these temperature fluctuations, scientists can gain insight into the initial conditions that led to the formation of the large-scale structure of the universe. In addition, the cosmic microwave background provides crucial information about fundamental cosmological parameters such as the density and composition of the universe. By analyzing its spectrum, researchers can estimate the amount of ordinary matter, and dark energy that make up the present-day universe. These measurements have led to significant progress in understanding how these components interact and influence the evolution of the universe. In addition, the cosmic microwave background radiation is important for theoretical models such as inflationary theory. According to this theory, the rapid expansion of the universe occurred early in its history, smoothing out the initial irregularities. The observed fluctuations of the cosmic microwave background confirm the predictions of inflationary models, supporting the idea that this event played a crucial role in shaping the properties of the early universe. The cosmic microwave background radiation is thus a cornerstone of modern cosmology, providing a direct link to conditions that existed shortly after the Big Bang. By continuing to study this relic radiation, scientists are furthering their understanding of the origin, evolution of the universe, and the fundamental forces that shape it. Gravitational waves represent a novel way for scientists to explore the mysteries of the universe, including potential states before the Big Bang. Spawned by some of the most violent and energetic processes in the cosmos, such as the collision of black holes or neutron stars, these ripples in spacetime carry information about their origin that is often not obscured by other interfering light, such as dust and gas. One of the most interesting aspects of gravitational waves, they can encode information about the very early universe, especially during epochs such as cosmic inflation. The rapid exponential expansion of the universe is thought to have occurred during inflation in the fraction of a second after the Big Bang. If gravitational waves originated in this era, their characteristic features can provide insight into the energy scales of inflation, the dynamics of the early universe, and the fundamental physical conditions that existed before the Big Bang. Current and future gravitational wave observatories, such as LIGO and the upcoming LISA Space Observatory, aim to detect these primordial waves. Their detection will not only provide valuable confirmation of inflationary models, but may also indicate the characteristics of the fundamental forces that govern the evolution of the universe during that period. For example, gravitational waves can indicate a potential energy landscape driving inflation, and even hint at certain symmetries in physical laws that may have existed. In addition, researchers are investigating whether gravitational waves may contain clues about the transition from the quantum realm to classical behavior in the very early universe. How the universe emerged from this quantum state and how spacetime itself was transformed can also be accessed through gravitational waves, helping to bridge the gap between quantum mechanics and general relativity. Gravitational waves have the potential to provide deep insights into conditions that existed before the Big Bang. By studying these ripples in spacetime, scientists will be able to unravel fundamental questions about the origin of the universe, the mechanisms that governed its rapid expansion, and the very nature of the forces that shaped our cosmos. As detection capabilities develop, gravitational waves may open new windows into the early history of the universe, expanding our knowledge beyond current observations. Testing theories about conditions before the Big Bang presents a unique challenge because we face constraints dictated by both the nature of the Big Bang itself and the field of modern physics, which includes quantum mechanics and general relativity. However, scientists use different observational strategies, theoretical frameworks, and experimental techniques to study these mysterious conditions. One approach involves studying the cosmic microwave background radiation, which picks up echoes of the universe shortly after the Big Bang. By analyzing temperature fluctuations, cosmologists can extrapolate details about the dynamics of the early universe, offering indirect evidence that provides a basis for theories that predate the Big Bang. These observations may help confirm or refute models of cosmic inflation or other scenarios that suggest special conditions preceding the Big Bang. Data from instruments such as the Wilkinson Microwave Anisotropy Probe and the Planck satellite have greatly expanded these possibilities. Another method is the detection of gravitational waves. As discussed, gravitational waves can provide crucial information about events and processes that occurred during the formation of the universe, and possibly shed light on conditions preceding the Big Bang. Identification of gravitational waves caused by primordial waves, if it proves possible, will confirm specific models of inflation and pre-existing states. Theoretical work also plays an important role in verifying the conditions that preceded the Big Bang. Physicists are exploring concepts such as string theory, loop quantum gravity, and the equirodic model, which put forward different scenarios for the origin of the universe. These theoretical constructs can generate predictions that provide information about what can be detected in our modern universe. Comparing these predictions with observed phenomena allows scientists to assess the plausibility of different theories. In addition, laboratory experiments and high-energy particle physics using particle gas pedals such as the Large Hadron Collider allow us to investigate fundamental forces and interactions that were likely important in the earliest moments of the universe. By recreating similar conditions that existed shortly after the Big Bang, researchers can analyze the behavior and interactions of particles, which provides insight into the forces and elements that shape the universe. While testing theories concerning conditions that existed before the Big Bang is inherently difficult, the combination of observational astrophysics, gravitational wave research, theoretical modeling, and high-energy particle physics opens up various avenues to further our understanding. Through ongoing research and new discoveries, scientists are striving to build a holistic picture of the origin of the universe and the conditions that prevailed before the Big Bang. Particle gas pedals play a critical role in the study of physics before the Big Bang, allowing scientists to recreate and study extreme conditions like those believed to have existed in the early universe. These powerful machines accelerate charged particles to nearly the speed of light and collide them with each other, creating high-energy collisions that produce a variety of particles and phenomena. By studying these interactions, researchers can gain valuable insights into the fundamental forces and particles that governed the universe shortly after the Big Bang, and possibly in the moments before it. One of the key interests in pre-Big Bang physics is understanding the unification of fundamental forces. Particle gas pedals, such as the Large Hadron Collider, allow the exploration of energy levels that can shed light on how forces such as electromagnetism, strong nuclear forces and weak nuclear forces could have come together at higher energies. These experiments allow us to test theoretical models that predict the interaction of these forces under conditions similar to those of the early universe, and thus provide clues to unraveling the unification processes that may have occurred before the universe cooled and expanded. In addition, particle collisions can create conditions that mimic the high-energy environment thought to have been present during cosmic inflation, the rapid expansion immediately after the Big Bang. By studying the particles that formed and any potential signatures of the forces that emerged, researchers can gather evidence to support or refute various inflationary models. For example, they can detect hints of new particles or interactions that point to mechanisms that could cause inflation or support the idea of symmetry breaking when unified forces separate as the universe expands. In addition, particle gas pedal experiments can help scientists explore phenomena related to the state of the early universe, such as the formation of dark matter and dark energy. Understanding how particles behave under extreme conditions will help formulate hypotheses about the components that contributed to the evolution of the universe. High-energy collisions can also produce exotic states of matter, such as quark-gluon plasma, which can provide additional context for understanding transitions between different phases of matter in the early universe. Particle gas pedals are essential tools for studying conditions that existed before the Big Bang. By recreating a high-energy environment that reflects the formative moments of the universe, these facilities allow scientists to test fundamental theories, study the unification of forces, and explore the nature of the matter and energy that formed the universe. Through these efforts, researchers are gradually piecing together a more complete understanding of the origin of the cosmos and the mechanisms that govern its evolution. The anthropic principle raises intriguing questions when considering pre-Big Bang theories, primarily because it links fundamental properties of the universe to the existence of conscious observers like us. This principle exists in two main forms: the weak anthropic principle, which suggests that the observed values of the universe are due to the necessity for the existence of conscious beings, and the strong anthropic principle, which argues that the universe must have properties that allow for the emergence of life. When considering the anthropic principle in the context of pre-Big Bang theories, it is important to examine how initial conditions and physical constants affect the development of a universe capable of supporting life. Many pre-Big Bang theories, such as cosmic inflation or string theory, suggest the existence of a range of possible universes, each with different fundamental parameters. This leads to the concept of a multiverse in which our universe is just one of many, each with its own physical laws and conditions. Within this framework, the anthropic principle helps explain why we find ourselves in a universe that appears to be perfectly designed for life. We may just be living in one of the few universes within the multiverse that supports life. By applying the anthropic principle, researchers can explore how certain conditions that existed before the Big Bang could have led to the emergence of a universe with the properties necessary for life. For example, they can explore how certain asymmetries in the early universe or variations in fundamental constants can lead to the creation of a habitable environment. Such discussions can help refine pre-Big Bang theories by identifying measurable predictions that can be tested against observational data. However, the inclusion of the anthropic principle is also fraught with difficulties. Critics argue that it represents a form of circular reasoning, where the existence of observers is used to explain the structure of the universe. Thus, while the anthropic principle can guide theoretical reasoning, it must also be complemented by rigorous scientific research and empirical verification. This means that any pre-Big Bang theory inspired by the anthropic principle must be based on observable phenomena and rigorously tested. Ultimately, considering the anthropic principle in the context of pre-Big Bang theories contributes to a broader understanding of the origin of the universe. It encourages scientists to investigate how the initial conditions and potential scenarios of the multiverse may have affected the fundamental properties we observe, allowing researchers to seek deeper connections between cosmology, theoretical physics, and the existence of conscious life. Current technology has a number of limitations in exploring the earliest moments of the universe, especially those that occurred just after the Big Bang. One major problem is the impossibility of obtaining direct observational data on the very nascent universe itself, since it was obscured by a dense hot plasma that did not become transparent to radiation until 380,000 years after the Big Bang. Consequently, we are left to analyze circumstantial evidence, mainly through the cosmic microwave background radiation and the large-scale structure of the universe, which only give us a glimpse of the conditions of the early moments of the universe. Another limitation is the energetic scale required to recreate conditions similar to those in the early universe. The energies of particle interactions that characterize the moment after the Big Bang far exceed the capabilities of today's particle gas pedals. While facilities such as the Large Hadron Collider provide extensive data on high-energy processes, they cannot yet probe the extremely high-energy regimes associated with phenomena such as cosmic inflation or the unification of fundamental forces. In addition, our current observational instruments are limited in their ability to detect more subtle features associated with the early universe. For example, it is expected that primordial gravitational waves generated during inflation may carry crucial information about the formation of the universe. However, the sensitivity required to detect these waves is beyond the capabilities of our current telescopes and detectors, especially for very long wavelengths that indicate inflationary processes. Upcoming missions can work to improve this sensitivity, but until they are operational, our ability to study these early moments remains limited. In addition, theoretical frameworks continue to push the boundaries of our understanding of pre-Big Bang physics, but many of these theories lack definitive experimental confirmation. For example, concepts such as string theory or loop quantum gravity offer great insights into the nature of spacetime and the origin of the universe, but remain largely untested in laboratory and observational settings because of the energy scales and environments they propose. Connecting these theoretical ideas with empirical data remains a major challenge. Although technological advances have expanded our ability to study the origin of the universe, limitations in direct observations, energy scale capabilities, sensitivity to primordial signals, and empirical confirmation of theoretical models point to continuing challenges in studying the earliest moments of the universe. It is hoped that as research progresses and new technologies become available, these problems will be addressed, expanding our understanding of the fundamental beginnings of the cosmos. Dark matter plays a critical role in our understanding of the earliest states of the universe, allowing us to understand the structure and evolution of the cosmos shortly after the Big Bang. While dark matter itself remains elusive and has not yet been directly detected, its presence can be inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Understanding how dark matter interacts with the other components of the universe helps shed light on the conditions that prevailed during its formative moments. In the earliest states of the universe, just after the Big Bang, rapid expansion and cooling processes produced primordial particles. These particles include ordinary matter, protons, neutrons, and electrons, as well as dark matter particles whose exact nature is still unknown, but are widely believed to be non-baryonic and fundamentally different from the matter that makes up stars, planets, and beings like us. The interaction of dark matter with ordinary matter probably played an important role in the formation of the initial density fluctuations that later evolved into galaxies and galaxy clusters. The significance of dark matter becomes particularly clear when studying the cosmic microwave background radiation. Fluctuations in this radiation provide a glimpse of the universe about 380,000 years after the Big Bang. Analysis of these fluctuations suggests that dark matter must have contributed to the gravitational wells that facilitated the cohesion of ordinary matter, leading to the formation of the first structures in the universe. This interaction between dark and ordinary matter has contributed to the evolution of the universe, influencing the patterns we observe today. Moreover, observations of large-scale structure show that dark matter drives the behavior of galaxies and galaxy clusters. The gravitational influence of dark matter helps explain the rotational velocities of galaxies that would otherwise not match the observed distribution of visible matter. This influence provides important clues about the distribution of matter in the early universe and helps to reconstruct the chronology of cosmic evolution. Dark matter is integral to our understanding of the earliest states of the universe, influencing the formation of structures, density fluctuations, and the overall dynamics of cosmic evolution. By studying how dark matter interacts with normal matter and affects large-scale structures, researchers can gain valuable insights into the processes that occurred shortly after the Big Bang and deepen our understanding of the fundamental forces that govern the cosmos. The distribution of galaxies provides important clues about the conditions that existed before the Big Bang and allows us to understand the processes that shaped the universe shortly after its formation. By analyzing the arrangement of galaxies in space, scientists can infer the underlying structure and dynamics that governed the early universe. This research is primarily concerned with the observation of the cosmic web, a vast network of galaxies, clusters, and filaments resulting from gravitational interactions driven by dark matter. One important aspect of the distribution of galaxies is that it reflects the initial density fluctuations that existed in the universe shortly after the Big Bang. When the universe became transparent to radiation about 380,000 years after the Big Bang, these fluctuations set the stage for gravitational collapse. Areas of slightly higher density attracted more matter, leading to the formation of galaxies and clusters. Thus, the cosmic structure observed today is a snapshot of the results of cosmic inflation and the subsequent evolution of these initial density fluctuations. In addition, the large-scale distribution of galaxies provides valuable information about the expansion of the universe. The correlation between galaxy clustering and redshift measurements allows cosmologists to reconstruct the history of cosmic expansion and the influence of dark energy over time. By tracing the position of galaxies, researchers can model how gravitational interaction shaped the large-scale structure of the observable universe, hinting at the laws of physics and conditions that existed in the early universe. In addition, studying the distribution of galaxies helps us understand the role of dark matter. Galaxies tend to form at the edges of dark matter halos. Halo interactions affect how galaxies cluster and distribute into larger structures. By mapping the distribution of galaxies, scientists gain insight into the underlying structure of dark matter, which has played a crucial role in the formation and evolution of cosmic structures, reflecting the dynamics present in the pre-Big Bang state. Overall, the distribution of galaxies provides a rich source of information about conditions that existed before the Big Bang. By simplifying complex cosmic structure and evolution into observable patterns, researchers can gain crucial clues about the initial conditions that formed the universe, as well as the fundamental laws that govern its evolution. The location of each galaxy is a piece of the puzzle, helping to reconstruct the history of the early universe and the processes that drove cosmic evolution. The apparent fine-tuning of universal constants is a fascinating topic that touches on the very nature of our universe. Before the Big Bang, the conditions and rules governing the universe as we know it did not yet exist. However, theories based on the assumption that the specific values of these constants, which seem to be carefully calibrated for the existence of galaxies, stars, and life itself, may be due to a variety of factors. One intriguing explanation is provided by string theory, which posits that the fundamental building blocks of the universe are not point particles but tiny vibrating strings. This theory proposes a scheme in which fundamental constants may arise from the shape and size of additional dimensions that we do not encounter in everyday life. These extra dimensions could lead to a variety of possible constants in different configurations, hinting at a landscape of universes, each with its own set of rules. Another assumption that existed before the Big Bang is the concept of a multiverse. According to this theory, our universe is just one of countless others, each with its own constants and laws of physics. In such a multiverse, fine-tuning may be the result of natural selection among these universes. Only those in which the right conditions for the formation of structures and the emergence of life have developed will be available to our observation, making our universe appear finely tuned, when in fact it may be just one of many. In addition, there are models based on quantum gravity that suggest that the universe may have undergone a transitional period before the Big Bang. According to this view, classical physics and its constants may have arisen from the more fundamental quantum realm. The variability of constants during transitions may explain the fine-tuning we observe today, shifting the focus from mere coincidence to a deeper basis of reality that has yet to be fully understood. This interplay between theoretical frameworks and emerging evidence invites ongoing exploration of the very fabric of our cosmos.